Let us start our today's class with certain recapitulation of the last day's job. That is, we have discussing the modern water tube boiler itself. Now, what we have discussed yesterday, definitely yesterday, is water cooled. All the boilers, furnace walls are supposed to be water cooled, and it is named as water walls. Actually, due to the furnace is the integration of the total boiler or steam generation system is the integration of furnace, economizer, boiler, superheater, reheater, air preheater into the modern preheater. All these things. These are all the integral parts or component parts which are integral into a modern steam boiler itself. Now, water cooling is also required for sometimes for superheater and economizer compartments walls, because in order to cool a superheater even, there are certain portion of the walls which is supposed to be cooled, and walls should be kept in a within acceptable temperature, otherwise it will be too much heated, and too much heat is being disparted from the wall, and that will cause the life of the wall to reduce. Say various other screens, say screens, dwelling walls, these are given, and these are used here, such as the screen dwelling table. These are components are used for the water screen itself. Now we have three designs of the waterproof boiler. Next page. Type A is a boiler with natural air circulation, as in type A. What is that? Let us see. Uh, Now, there are three types A, B, and C shown in the figure itself. Type A is the natural circulation, as in the type as such as in type A below. The heat transfer in the water walls around the heat transfer to the water tubes around the walls is mostly radiation, the radiation from the fuel flame, and thus less by convection from the flue gases itself. Now, what is the source of heat? How the heat is transferred to the wall? Mostly it is by radiation, but and less by the convection, which means by conduction and convection, which means the flue gases directly doesn't come in contact with the walls itself, but their heat energy produced by the flue gases are simply transferred to the wall itself by means of the radiation itself. The heat transfer to the mostly natural circulations are used up to steam processes. Natural circulation used up to steam, say around 180 bars, not to that high pressure boilers, not to the supercritical boilers, etc. With the operation of steam here, with steam from water taking place in the boiler drum itself, with separation of the steam from water takes place in the boiler drum itself. Here, where is the boiler drum? Here, these pipes are defined generally as the boiler drum itself. Now, what happens here? Uh, Natural circulation. Now, boilers with forced circulation by a special pump called a Lamont boilers is shown in point B. Here we are having a boiler feed pump itself. Here we are forcing the boilers through the economizer wall, and then goes to the boiler drum, and there it is separate. It is again sent back to the preheater itself. I mean the riser. It comes back down to the downcomer, goes to the from the header to the riser, then goes back to the drum itself, and from the drum it is sent to the superheater itself, where there is no boiler pump somewhere. If there is no boiler pump, this is one another design for the natural circulation. Here there is a valve. A boiler pump is also shown here. There is a valve here, and here it is goes to the through the pipe by the economizer directly to the economizer, then directly to the bulb itself. Now, they suffer a certain amount of freedom. Uh, The boilers are forced circulation by a special pump called Lamont boilers. They offer a certain amount of freedom in the arrangement of evaporator tubes and the boiler drums itself, evaporator tube and the boiler drum itself. Now, such boilers can be adapted to limitation in height and space. Actually, they are suitable for steam pressure up to 200 bar. Boilers can be designed to operate at pressure above the critical pressure and 221 bar, and no drum is necessary. No drum is necessary in such cases as there is, which is called once through the boiler. No drum is necessary here because there is no mixture of water and steam. Water is directly converted to the steam, and there is no circulation of the steam and water vapor and steam mixture. The water enters the bottom of the tubes and completely transforms to steam by the time it reaches the top. Here, by passing through the tubes only once. For this, it is known as the once through boiler, then referred to as drumless boiler, also referred to as drumless boilers. It is type C as well as type C and D. Here, here the three circulations are so. In brief, there are three circulations here. One natural circulation where there is a drum where the natural circulation where there is a drum where the mixture of water and water vapor is housed, and through the down common it comes down common tubes, it comes down to the header of the riser itself, and from the riser it goes back to riser, which is inside the furnace wall itself, where it is mostly converted into the steam and go back and going back and accumulated in the drum itself, where it is separated and then the steam part is sent to the heater itself, which is shown here. Here is the one is the boiler drum here. One is here the boiler drum. It is here particular one boiler drum here. Here the tubes are from here, comes to this drum, come to this header itself and goes to the riser itself. Again come back to the drum, and from the drum it goes to the it goes to the number 2 is the separator from the gun. From the drum, it goes to the riser, to the superheater itself, where drum steam separators 2, number 2. No, it is not steam separator. Boiler fill pump is here, and circulation pump is the number 4. So in the next cases, there is a forced circulation type where we are using a pump which is called boiler feed pump itself, which sends the boiler to the economizer, to the 5 or economizer himself, and there from to the drum. From the drum, it comes back to the through the downcoming tubes to the separator itself, and goes back to the riser, and then goes back to the drum itself. From the riser, it's sent to superheater and goes out superheater itself. And there is a supercritical boiler which is called once through boiler, where there is no drum is required, because boiler is especially is raised over the critical pressure, that is on 221.5 meter bar, and there it sends from there. From there it sends to the supercritical, and to the superheater and superheater itself. Now, next, now here we are showing the schematic flow diagram of a common natural circulation steam generator itself. water here at 170 degree centigrade to 260 degree depending on the boiler pressure from the high pressure feed water enters into the economizer and leaves saturated or as a two-phase mixture of low grade low quality. So here temperature is less than supercritical. Supercritical is a 221.5 and water is heated at about 270, 170 to 260 degrees centigrade, depends on the pressure itself. But it is not pressure here, whatever it may be, but below the supercritical pressure himself. Now, from the high pressure feed water, heater again enters into the economizer and leaves saturated or as two-phase mixture of low quality. Here high pressure feed water and got the some temperature from the economizer itself and but not totally it is boiling the boiling the water. So here it is there is a steam and water vapor mixture is left the economizer itself. This quality is not that good. It is not fully maybe two-phase mixture of low quality itself. Maybe it's not fully saturated with steam itself. Then enters the drum at the midpoint lengthwise, which are situated outside the furnace to headers. Now, through headers are connected to the water pipes, water tube that line of furnace walls and acts as a riser itself. Here we follow the same thing where from the drum it goes down to the drum comer, then goes to the riser itself, riser inside the furnace and furnace which hits the water steam vapor and air mixture as air mixture to convert it into vapor itself. Riser in the riser tube receives heat mainly uh, from the radiation of combustion gases and boils. Mostly the heat is always available by radiation of the gases, means the heat generated is transmitted to the walls of the tubes itself, but it does not come directly to the boiling frame or burning frame of the fuel. The density difference between the water in the water outcome or that in the riser helps the circulation itself. So it is follows the principle of natural circulation as water has much more density of the water is more than the steam. The mixture of water and vapor is heavier than the steam itself. So it comes down through the downcomer tubes and goes to the riser by the natural flow by the weights of its own density and weight, and thus it helps the natural circulation. The steam is thus separated from the bubbling water in the drum and they goes to the convective or primary superheater itself, where heat absorbed by convecting mode from the coiler absorbed by convective mode, and from the convective superheater steam goes to the radiant superheater. So there is we are having convective where we are comes directly contact with the flame itself and then goes to the radiant supervisor where it comes to the exposed to the heat of the flame itself. It's shot to the top because it is installed at the top of the furnace where heat absorbed by radiation himself. The steam leaving the radiant superheater goes to the superheater. Now where water of high purity is sprayed on the steam to bring down the steam temperature. So from radiant superheater, there is another operation. The another mixture is desuperheater. Means this temperature we should come in within our required limit, not more than that. So we spray cold, high purity water to the steam itself. Then steam temperature, we kept to the desired level, not more than that. And from the deep superheater, the steam finally goes to the pendant superheater for further superheating before it leaps to the main stop valve to the high pressure turbine itself. Both RSH and PSH are often termed as secondary superheater, and steam existing the high speed turbine HP turbine goes back to the furnace for being superheated to the desired temperature in the reheater. Steam after being reheated flows to the intermediate pressure turbine for further expertise. Now, what is clear here? We have superheater. We have primary superheater which is being heated by the convection mode, and secondary and radiant superheater which is being heated by the radiant heat by radiation. Means primary superheater comes in contact with the flames and react transmission of heat, where secondary superheater radiant supervisor got their heat at the by the radiation of the heat generated inside the furnace wall itself. Now, steam again after supervision before going to the turbine itself go to a desuperheater because we have need a proper control of the supervision, proper control of the superheat itself. Now, where the heat is absorbed by the steam temperature, we have to keep it to that level by means of spraying a pure cold water to the superheated steam to thus bring it to the required level and should have a control over its particular temperature itself. Then it goes to the pendant superheater for further heating before it leads to the main stop valve. So we have three stages of superheating: primary, that is primary, radiant, and pendant superheating for before it's sent to the main stop valve to the high pressure turbine itself. Then both radiant and pendant supervisors are superheaters, sometimes called secondary superheater, and steam existing from the high speed time goes back to the furnace for being re-superheated for the desired temperature in the reheater system. After being reheated, flows back to the intermediate pressure turbine for further expansion. So we are not uh, throwing out the steam after from the turbine itself. It is again recirculated through supervisor and reused after that. Next, the atmosphere heater fed by a forced draft FD fan is preheated by the ongoing gases in the gas exchanger called preheater. Now, we require gas for we require air for burning or burning the fuels. We require oxygen of the air. Actually, we use the atmospheric air, and we generally preheat it by the preheat heat exchanger defined as preheater, air pH. Air heated to the desired temperature generally varies as per your requirement. It can be as high as 250 to 200, 400 degrees centigrade, depends on the type of the coal burn, and is split into two streams, primary and secondary stream. Hot primary air, mostly it is 30 to 30% of total air, goes to the pulverizer to dry the coal. Then so a portion of the air, say around 30% means one third, it sends to the pulverizer itself, where the coal mostly which is received as a wet condition is totally dried by means of this hot air itself. And it requires, and this helps the better grinding, also help the coal particles to the burner itself. Mm, mm. Now, so a portion of the air, which we are first, what we are doing, we are reheating or preheating the air to so that it helps us ensure the drying of the fuel itself, ensures the proper burning, proper quick burning of the fuel itself. And first of all, 30% of it is generally 15 to 30% sales to the pulverizer itself, where we are supposed to dry the coal properly because mostly the coal used we received mostly are wet, and get, we better grind it, and in the pulverizer it is totally it is converted into it is dried, and then you make it useful for better grinding and also to help the coal particles to the burners into the furnace itself. So coal particles, just the coal particles also mixed with the total coal itself, and it is dry. If you can dry it properly, you can simply send it to the burner without being making a paste on the walls of the furnace itself. And the secondary air, hot secondary air flows into the wind box to get it distributed to the burners. So there is a wind box we use, which is nothing but a accumulator of the hot air, and from it it is feeds different burners to help the combustion itself. Fuel burns in the furnace with great intensity to a with great intensity to some 1350 degrees centigrade or even higher. So quickly we have to burn the fuel in the furnace. Means fuel burns with the furnace means we have to burn it very quickly. We don't have the time to uh, first heated it, then ignite it, and then burning it like not like this. So we have to make it as quick as possible, because we have to get the temperature as high as 1350 degrees centigrade or even higher itself. Depend on the quality of the fuel. Just 1 second. Uh, Depend on the quality of the fuel itself. Now, the combustion gas impart the portions of their energy to the water tubes itself, water tube risers. So gases, after the burning of the fuel within the flame, they are creating a hot gases, hot smoke or gases, which is nothing but smoke and gases which exists from the burning coal itself, burning fuel or coal itself. Now it goes through and surrounding to the water tubes, the risers, and then to the superheaters, reheaters, and even economizers, and to live later at around 400, 450 degrees centigrade itself. So what we are finding here, first we have to heat the air, we have to receive the air, which is atmospheric temperature, then we have to preheat the air up to a certain temperature, so that a portion of it, means 30%, is again sent back for drying the coal, drying the fuel, which is coal, and as well as add the coal dust itself, which we can fit very easily to the furnace and can have it quick, have it immediate burning of its burning itself. And the rest of the about 70% of heated air goes to the furnace, which ensures quick and immediate burning of the coil itself, and should be burned and create a temperature say around 1350 or 1400 degrees centigrade, and so. But depends of course on the quality of before the ignition value of the fuel, but it is supposed to cool, heat it up to that temperature itself. Now uh, depend there what this coal is. Now after the burning of, when the coal is burning and more and more is fed into it, the coal after burning is created smoke and created gases or smokes, which is very high at some temperatures around 14 degrees centigrade or so. First it comes in contact with the riser, which comes from the downcomer headers, and from the drum, downcomers and headers, and then passes inside the furnace, into the form of tubes, passes inside the furnace. This hot gas or smoke, everything is being first hitting this uh, mixture of water and what vapor mixture, which goes through the riser and again goes back to the drum itself. Now remaining part of the heat, it then goes to the superheaters and reheaters again, and economizer, and thus air leaves it at about, at the economizer, the air that becomes, the temperature becomes reduced to 450 degrees centigrade itself. Next, what they're doing, they preheat again the atmospheric pressure in the APH, air preheaters itself. So after making so many films, we come back to the preheater itself again, so that it is again preheating the air itself, and then leaving it around 160 degrees centigrade. Then dust collectors and electrostatic precipitors collector and contain solid particles, mostly ash from the gas stream itself. So there is a flow of gas, which is a flow of air, then which is converted into gas itself. It's where is coming from the atmosphere, goes to the preheater, which is preheated, and 30% of this preheated air, 15 to 30% of the preheated air goes for drying the coal and the coal dust itself, and then sent to the furnace. Remaining 70% of the air goes to the furnace, and ensure that it's quick and immediate heating of the coals itself. And generally, there we have coal is heated and creating temperature around 1350 to 1400 degrees centigrade, which is supposed to be depends on the coal, but we have to keep it near it. Then the heated gas or heated smoke, everything along with it goes up and passes to the tubes of the riser, which carries the water and moisture, which other converted into steam and goes back to the drum. Then the fumes goes up and goes to the preheat, goes as superheated and then to reheaters itself, and then to economizer, and then comes back at the economizer. It becomes at the economizer. It becomes uh, just 1 second. Hello. Okay. Next, that heated air from the economizer goes back to the preheater. Again, it is preheated, preheating the incoming the, air, and then air, then generally leaving it at temperature of 160 degrees centigrade. So temperature for at furnace, it is started from 1350 degrees or 1400 degrees centigrade. Then the economizer, it becomes 450 degrees centigrade, and then it is air preheated. It becomes 160 degrees centigrade. Then it sends to the dust collector and statics electrostatic precipitors, where it connected the entire solid particles, entire polycycle most gas from the flue gas stream itself. And induced trap in the fans draws the flue gas from the furnace and send it to the through the stacks to the atmosphere. So we have a induced fan which is draws, which is created a pressure outside, which creates a lower pressure, which is created a pressure lower than the atmospheric pressure, and thus drawing out all the moisture, all the fumes and gases from the furnace, and sends to the stack to the atmosphere itself. The existing air gas temperature is not very less; it is around 160 degrees centigrade, which is the more or less same temperature where it is with which it is coming out from the reheater itself, and represents an availability loss to the furnace tank, but it is accepted because of the following reasons. This heat, it has a considerable amount of heat, is 160 centigrade, which is considerable, which we can reuse it to a certain extent to improve the efficiency of the furnace, but we accept it due to the following reasons. The gas temperature itself should be kept well above the dew point temperature of the water vapor in the gases, equal to the saturation temperature at the partial pressure of the water vapor. The saturation pressure at the what is dew point? It is a saturation temperature, dew point temperature, saturation temperature at saturation temperature at the partial pressure of the water vapor to prevent condensation, which would form acids with SO2 and SO3 that could corrode the metal component in its path. First of all, this oil gas has contained sulfur itself. These flue gases, after the melting from the furnace, contains a considerable amount of sulfur. This should be this temperature should be well enough, should not react and form the acid with the reactant from the hydrofluoric H2SO4 and sulfuric acid and other H2SO3 with the air itself. So this if the creation of this type of acid will greatly corrode the metal components in its path, and it will lose its shape itself, lose its life itself. The flue gas must must have enough buoyancies to rise in a high fume above the stack for proper atmospheric dispersion. So the flue gas, what is the flue gas which is flash generated from the after fuel after it's burning? It should have enough of buoyancy. It should have enough buoyancy so that it can be buoyant enough to move up, and through this stack it goes to the atmosphere itself. From the dry bottom furnace, the clinkers fell to the clinker grinder to be broken into pieces and then carried by water in a hydraulic sluice where also falls the gas from the dust collector and then is precipitated. So all this dust created by the film by burning the coal is uh, or to the clinker grinder to be broken to proceed, and all the dust particles are broken up to a certain limit, not to a very big high volume of dust, and it should be a small metal of glass and then carried to by water in a hydraulic sluice where is also falls the gas from the dust collector and their precipitators. Next, we are coming to the item known as economizer. Let us discuss what is the economizer itself. And economizer, what we have discussed so far, is the function of the boiler and the function of the air which is being used. First of all, where this water after the steam goes, and where how we are using the incoming air for burning and other flow for burning of the fuel and other what was done by preheater itself. In a boiler, we have furnaces where we are supposed to put your fuels like coal, and you have to put feed with air for to feed the oxygen along with it, so that it can be a quick and reasonable burning. To ensure quick and reasonable burning, we are heating the air by on preheater and up to a temperature of 460 degrees centigrade, and then send it into the flue gas itself. A portion of this preheated air then sent to dry the coal before it sent into the furnace itself. The furnace, by the action of this hot air, it quickly burns and as quick as possible, and it should be burned within a moment, so that it is creating around 1400 degrees centigrade inside the furnace itself. This temperature, this high heat, is flows by means of the gases and smoke coming out of the furnace itself. It is heated the riser walls of the drum, then goes up to the superheater, different superheater as one after another, and then a portion superheater, de-superheated, secondary superheater, then it goes back again to the air heater, where it is again transferring heat, remaining heat to the air as well as to the oxygen itself. But there are few reasons that still it has temperature around 460 degrees centigrade, which is sufficiently high, so that you should have to use it in somewhere. So it has certain problems, so that you cannot create drop the temperature from to the air itself, from this amount itself. Next, we are starting goes to the economizer. Economizer is the heat exchanger which rises the temperature of feed water, leaving the highest pressure feed water heated to about the saturation temperature corresponding to the boiler pressure. So what is this? It is a economizer. It's a big name, which is one of the most useful part of the total system. Is a heat exchanger itself, which it transferred heat from surroundings to the incoming fluid, which going through the heat exchanger itself. Now, what happens? An economizer is a here the feed water is leaving the highest pressure feed water later to about saturation temperature and correspond to the boiler pressure itself. So what we are doing, the highest pressure feed water heater, this temperature is it is rising the temperature of the water by using the heat of the fumes or gases coming out of the boiler itself or from the furnace itself, and temperature of the feed water is rising, leaving the highest pressure feed water to about the saturation temperature corresponding to the boiler pressure, so that it temperature rises to the saturation temperature where according to as per the boiler pressure. So here the moisture will totally saturated into the flow of into the flowing water itself, and this is done by red flue gases existing the last superheater or preheater at a temperature of varying from 70 to 75 degrees centigrade. So how it is sitting, it is getting hot flue gases coming up with last supervisor or reheater, then this goes to the economizer. The economizer was used because throwing out such high temperature gases involves a great deal of energy losses. So utilizing these gases in preheating the feed water, then higher efficiency and better economy or acid. So what is economizer is doing? It is improving the efficiency of the boiler itself by converting a lot of converting the heated fumes or gases at which is at very high temperature, 370 degrees to 550 degree, and using this to rise the temperature of the running water to the saturation temperature, so that it can be easily and quickly converted into heat in the superheater itself or in the boiler itself, boiler drum itself. So yes, it is thus absorbing a considerable amount of energy in the from the boiler drum. Now, these gases in the free heating water temperature, by these gases in heating water preheater, higher efficiency and better economy which are achieved. The economic tubes are only 45 to 70 millimeter in outside diameter and are made in vertical with coils of continuous tubes and connected between inlet and outlet headers. So again, that header means the box. It's a complete analytical, complete integrated box where which houses the tubes, and from one end there is a heater, and other end also there is another header, and which is housing the ends of the tube so that it can distribute the flow of, I mean, it's water carrying water or stream from inlet to outlet itself. So there are economic tubes are mostly 45 to 50 centimeter, around 5 centimeter in diameter, not very big, in made in vertical coils of continuous tubes. So that which is tubes is continuous connected between the inlet and outlet headers, which each section forms into several horizontal paths connected by 180 vertical bends. So supervisor initial economizer has connected to the highest heat and connected through the two headers, inner incoming and outlet headers, and each in several horizontal path. Then it connected goes to vertical by making 180 vertical bends. The coils installed at a pitch of 45 to 50 meters spacing, which depends on type of fuel and ash characteristic itself. The coils inside at a pitch of 45 to 50 millimeter spaces. Now, figure below what shows the economizer and the temperature profile of the flue gas and the water related saturation temperature. What is showing here? This is inlet of the water. There is a pump, and the feed water has a temperature. Feed water has a temperature itself. Feed water has a temperature of say around TFW, through which it is coming inside the economizer tubes, and the gases, the omega G is coming over it and goes out after hitting the matter, and through these spiral shaped tubes the water vapor mixture goes up and becomes converted into steam, and where it comes out with saturated temperature of water and steam, where steam with water is totally converted into the water itself. That is a header outlet, is a header inlet header. Means there is a number of tubes which are one end is connected to the inlet header and other end is connected to the outlet header, and through all the tubes inside water content are being heated by the coming heated gas itself. Now what happens to here? Let us go. Just 1 second. So what we are getting, the rate of heat transfer of the flue gases to cold is given as Q economizer. The amount of heat goes to the economizer itself, omega G into CPG. Omega G is the density of the gas itself, is the specific heat of the gas multiplied by Tg1 minus Tg2, where omega CF2, where or which is equal to omega F water, feed water going up, specific heat of going up feed water multiplied by the temperature of saturated stream multiplied by temperature of saturated feed water itself, or which is equal to uh, U0 A0 into delta Tm, where delta L into m is log mean of the temperature difference. Delta L is the log mean of the temperature difference, which is given by delta Ti into delta Te divided by log E to delta Ti by delta T. This delta Ti, where Tj T1 and minus T gas. What is the gas temperature of the gas minus saturation temperature? And temperature of the economizer, it should be temperature of the gas at the outlet minus saturation temperature. And 1 by U0 A0 is equal to 1 by HSC in the AY plus 1 by H0 HI HI itself 1 by HIAI plus XW KW into ATM in plus 1 by H0 A0 plus 1 by H0 A0. Where what is U0? It is overall heat transfer coefficient, and HSC heat transfer coefficient to the HSC is the heat transfer coefficient due to the scale formed on the inside of the tubes, and HI, the inside heat transfer coefficient. These are all heat transfer coefficient. All these HI, HC, these are all heat transfer coefficient itself, and KW, thermal conductivity of the wall itself. Now, uh, AI pi d n pi di into L is the pi di is the surface of the economizer multiplied by the number of the tubes multiplied by the length itself, and H0 is equal to n pi d0 into L length of one coil, n number of coils, A and M log mean area, H0 minus 1 just given above, and XW uh, thickness of the tube wall, HF0 the heat transfer coefficient due to the solid ash and full, so the outer surface of the tube, and H0 heat transfer coefficient of the outside film. If the resistance due to the scale 1 by HSC A1 and fouling 1 by HH0 A0 are neglected, including the time to be cleaned, including them to be cleaned, and if the wall thickness is small, then the overall heat transfer coefficient reduced to 1 by V0 is equal to 1 by H1 plus HXHW divided by KW by 1 by H0 itself. Uh, then the gas side coefficient is much less than the water side heat transfer coefficient. That is H0 is less than HI. To compensate this, the outer surface of the tube may be finned to increase the surface temperature of the heat transfer. Both gas and liquid flow water are force connected convection, which is NU F RE into PR, where Nu is the Nusselt number, Hd divided by Kf, Re Reynolds number, Jd divided by Vf. Vf is the kinematic viscosity of fluid, Pr is the Prandtl number, Cf by Pv, and Kf. Mu f is the dynamic viscosity of the fluid, Kf the thermal conductivity of the fluid film. If the flows are turbulent, the Peters boiler equation can be used to evaluate heat transfer coefficient as below. Nu is equal to 0.023 into Re to the power zero point 0.8 into Pr to the power n, where n 0.4 if the fluid is heated and n is equal to 0.3 if the fluid is cooled itself. With the help of the equation 3 and 4, H0 can be estimated, and from equation 1, the surface area need to be ascertained, where H0, since the fluid is flowing through the tubes at exit from the economizer with water being saturated, and the equation forms takes this particular form. Okay, so far I am ending this class here.